Hello, welcome to Debug School. This time, reading error messages part 2. Remember this big intimidating blob of text? That's called a stack trace, and it is a big reason why error messages look so scary, especially for beginners. But if you want to get better, you have to face your fears. And so this time, we're going to focus on how to read the stack trace and get the most out of it. What are stack traces good for? When a runtime error occurs, it occurs at a certain location in the code. Usually, it has an accompanying stack trace. The stack trace tells you how the code got to that place. And there are a few situations where reading the stack trace is helpful. 1. When you determine the mistake is not necessarily in the function where the error location lives, but rather in the way or in the context in which it was called. 2. When the location of the runtime error is not in your own code, but inside of a third-party library or framework. But before we get into how the stack trace helps us with those things, let me show you what it is. Imagine if you were the JavaScript interpreter, and you were responsible for executing this JavaScript code, and all you had were a pencil and a piece of paper. How would you go about it? Well, let's see. First, I would use a little arrow marker to indicate the current line of the program that I'm executing at any given time. This is technically called the program counter. So I'm going to start on line 1, and here a variable named result is declared. In order to remember its value, I'm going to make a storage area for it, which is just a 2-column table where the left column is the name of the variable and the right column is its value. Now, what's the value of the result? Well, result is being set to the result of a function call, and that means that before I get the value, I need to evaluate that function call first. To do that, I need to move the function pointer to the start of that function, namely the square of difference function, and that is line 9. But I need to remember to come back here to line 1 when the function call completes. So line 1 is called the call site. It is the location where a function call was made. So to help me remember where that is, I'm going to write down line 1 here. I'm also going to write down the way in which the function was called here so that I have a reference of what the call parameters are. So now we're good to go in the square of difference function. First, I need to make some space to store the function parameters. I have x and y, and their values are taken from the call site, and those are 4 and 7. Then, moving on to line 10, here we declare a variable div, which takes on the value of x minus y. That's 4 minus 7. And what is the value of 4 minus 7? That's right, it's negative 3. Moving on, we declare a result variable. In order to find out its value though, we have to make a function call to the square function. So square is declared here on line 4. I will jump the program counter there. But first, let me make space for the result variable. Okay, now I will record the location of this call site, and that's line 11. And I will also write down the invocation of the function call, square of negative 3, as negative 3 is the current value of div. In the square function now, I will first make space for the parameters of that function. There is just one parameter, n, and it has the value of negative 3. Next line, the variable result is declared, and it is set to the value of n times n, which negative 3 times negative 3 is, what is it? That's right, 9. The next line just returns the value of the result, which again is 9. So with that, we can resolve the function call square of negative 3 to the value 9. So where do I go now? Oh, line 11. It's a good thing that I wrote it down. I have a terrible memory. Since this function has returned or has terminated, I can now clear out its variables because we no longer need it. So back on line 11, we were waiting for the value of result, which we now know is 9. In the next line, we just return this 9 again. So I'm going to say that the call to the square of difference function also resolves to 9. Now I go back to its call site, which, as I wrote down here, is line 1. And I can now also clear out the variables for this function call. On line 1, result also gets its value, which has been resolved to 9. And then the next line after that, console.log prints result is 9. And there we have it. We have walked through this program line by line, manually, by hand. But I made you go through all of this, and I still haven't told you what a stack trace is. Don't worry, I'm going to tell you right now. Let's rewind to here, and let's say that there is a mistake on line 6 of the program. In that, the variable result was misspelled. What happens? Well, the program must halt because the variable result doesn't exist, and therefore there is no way to return its value. We have to call it quits, and we're going to output an error message saying result is not defined. But we could do better than that, because look at all this information here on the right. If we give the programmer this information, it could help them figure out what went wrong and how things got this way. Most programming environments, JavaScript included, will print out the series of line numbers in this stack in reverse order. In our case, it will look something like this. With this information, the programmer who encounters this error and has to debug the program will know what the series of function calls that occurred were, which led to the error. Now, let me show you an actual stack trace. I will pick up where I left off in reading error messages part 1 with the Bob exercise. I have secretly added some code to Bob's test suite, which may or may not cause things to break. Let me run the tests. And that's an error. Input trim is not a function. The error location is bob.js line 4. And here is calling the method input.trim, which should be okay if the input is a string, because strings have a trim method, in newer browsers anyway. So possibly what's happening is that the hey method was called with something other than a string as its first parameter. Now, there are a few different ways to test this hypothesis, but with the stack trace already here, I can look down to see where the method was called from. The next line in the stack trace is bobtest.spec.js line 90. So bringing that up shows that this line, as it turns out, the hey method is in fact being called with an object as its first argument. So my hypothesis was correct. We can verify this further though by swapping in a string here and see that the error goes away as a result. And it does. Now to fix this test, if it were a requirement, we might add a conditional that says if the subject is not a string, then just return the string whatever. And that passes. So the lesson is, if looking up the location of the error doesn't give you enough information to figure out the problem, sometimes drilling down further into the stack trace will. Now I want to dig deeper into this stack trace. The next location is jasmine.js 1064. This is the source code from the Jasmine framework, and you can view its source code just the same. This is the line in question, and it is calling this.func using the apply method of function, which is just a fancy way of calling a function while also setting its context within it. Now, which function do you think this.func is? The answer is found by going back up a line in the stack trace, and we're back in this test case. So since the line number is 90 and it belongs to this function, this function must be the function that was invoked on the stack trace line below it, i.e. this.func. Similarly, when the hey method was called here, we can find the location where hey is defined by going up a line in the stack trace. And now we're looking at Bob's definition of the hey method. Now let's go even deeper down the stack to Jasmine.js line 2096. And we see here that this is where the execute method that we just saw here is called. We see something like an array of blocks here. Let's go down even deeper to line 2049. And here we see a start method being defined in a sort of queue object, which presumably is called to initially start running all of the tests. And if we go even deeper, we see the place where the start method is called. I could keep going if I wanted to, but I think you see that this is a chain of events which you can follow backwards one by one. And it's almost like going back in time, that you can reconstruct what happened and how things got to where they are when the error happened. And that is really cool. What's also really cool is that by looking into the stack trace and looking up the code locations, you can actually dig into the internals of the libraries you're using and be able to figure out what they do and how they do it, as we have already started to do with the Jasmine testing framework. I mean, we've already learned that there is some sort of queuing mechanism for running the tests, and presumably each test case is an item in that queue to be executed sequentially one by one, maybe. Understanding and working with third-party code, although it seems intimidating at first, is actually a very powerful technique for debugging. And I'm going to cover that in more depth in a separate lesson. I'm also going to talk more about the call stack in the lesson on using debuggers. This concludes the lesson. To help you retain this information so that you can actually remember to use it when you need it, I have prepared a couple of exercises for you. Please do them for your remembrance. Until next time.